Today I will be wrapping up our earlier discussion and about random walks. And I think I left with you a problem, the gambler's rune. I don't know if you guys had a chance to have a look at that problem as well. Oh, by the way, this session is being recorded, and you can watch previous recordings on our Momentum Learning YouTube channel. So yeah, that's a pretty good channel where we are planning to put all the material as a repository over there. Okay, so let's start with the homework probably. So that would be a nice way to start the class. Let me make sure I have my blue color. Yes, there you go. So gambler's rune. Well, the question is, let me make a modification to the problem that I asked last week. And don't worry, we will be able to solve that very problem as well together. Wow, we're about to hit 300 participants. That's good. All right, so the question, one version of the question appeared on the Mandelbrot. Let me remind you of that version of the problem which appeared on the Mandelbrot contest. Why, we have 300 now. All right, so the problem is the following. You and your friend, you are playing this game where each one of you starts with, I think the Mandelbrot question was $14. You have $14, your friend, also have $14, and you start repeatedly flipping the coin, flip coin repeatedly. And if suppose that I win if it comes up heads, and you win if it comes up tails, and each time I win you give me $1, and each time you win I give you $1. So the idea is we will stop playing when one of us will have no money left. The question is how long until we will run out of money. So head, me, my situation, I get one, you lose one. And tail, if it comes up tail, I lose one and you win $1. And the game ends, let me repeat the game, and game ends when one of us runs out of money, And the question is how long until one of us will run out of money. So how many times will we keep flipping this coin, right? How long until one of us out of money? Or meaning how long, how many steps will the game last? Anyone knows the answer? Yeah, much more than 28 probably, right? Because I'm assuming that this is a fair coin. Probably not infinitely. Yes, okay, so a couple of you already know the answer. Good, yes. The answer is 14 square, or 196. So let's have a look at it together. And then we will realize that the tools that we develop can do even better. What if we didn't start with an equal number of money? Usually that's the case in real life situations. We have different amounts of money. So what is the probability that I will win before my opponent wins? Here, because it is symmetric, I have a 1/2 chance of winning and my opponent have a 1/2 chance of winning. So the probabilities are easy to calculate due to that symmetry. That's why the question is worded in a way such that it's asking for the expected number of flipping, right? How many times it will be flipped. So this is an expectation question rather than a probability question, because we start with symmetric probabilities, 1/2 chance I win and 1/2 chance my opponent wins, because it's a fair game basically, right? All right, so with this wording of, with this variation of this is a simple variation of that problem. So the way we can do it is, and before I solve it, probably it might be one more time just to be on the safe side. So this is 0, this is 14. One way to interpret the problem is as if we both start at 0, and each time it comes up heads, I make a right turn, which probability 1/2. I'll go 1 to the right, and with probability 1/2, I will go 1 to the left. And so this is, I think, a similar, and the game ends when either I reach at that point or this point. Do you guys agree? So in a sense, this is me winning cumulatively $14, and here me losing cumulative $14. So this line represents my outcomes, right? So here I win. Why? Because I end up with 14 plus 14, $28. And here I lose. So it's all me, right? I lose. How do you write lose? I lose, meaning I started with 14, but then I lost $14 along the way, and $0 left. Does everyone agree that, well, the game, we might end up in a very unlucky situation where we keep traveling somewhere along this line, never hitting minus 14 or plus 14 along like that. But this is a zero probability event. So ultimately, we will hit that plus 14 or that minus 14. Well, to be honest, the calculating, well, okay, all right. So some variations of this problem can become very challenging. So that's why I should be careful when I say the individual probabilities and so on. But I think we are in pretty good shape. So I think last time we came up with some very good idea. Remember the last week, I believe, we played different variations of this game where there was a line and we played multiple variations. In one variation, we were either jumping 1 or 2 with equal probability, each one, 1/2 or 1/2. And we asked, what is the probability that we will hit 1,000? We will not run over it, right? So we will exactly hit 1,000 when we are approaching it that way. And we came up with an answer very close to 2/3. Another variation of this we played where there was a frog starting at 0, either 1/2 chance it makes a jump 1 unit long, and 1/2 chance it makes a jump minus 2 units. Whenever it makes a left jump, it makes it 2 units to the left. And then we, based on this, we asked the probability that the frog will visit this one, and so on. So different variations of this same problem. You can check our previous lecture as well. But we will pretty much use the tool that we developed, and the tool that we developed is the following. So because it's an expected, so how long? So the question is asking for the expected number of flips, right? So I can do a positional argument, and it would be the following way. Starting at, it doesn't necessarily, we don't have to start at that 0 point, right? We can start anywhere. Indeed, the original last week when I gave it to you, it was I start at $10 and you start at $5, me winning. Actually, this is exactly what we want, right? So expected number of flips until, let me see, is this, yeah, dealing with negative numbers is annoying, right? So probably, okay, so I'm sorry, yeah. Well, it's the same thing basically, but if you think that, let me think, okay, you know what, I'll just, yeah, okay, let me just go back to the original formulation. Okay, this line, okay, I'm so sorry. Okay, this line represents all of my money. Okay, my money, I have $14 here to begin with. I can either end up with $28 or I can end up with $0. Either case, the game ends. Here, the game ends with me winning. Here, the game ends with me losing, but it doesn't matter. The question says how long until the game stops. Okay, so expected number of flips starting at any position. In this game, we are starting at 14, but we could have started at anywhere. We could have started with $3 or $10 or $20 in our pocket, right? So if I start with N dollars, the expected number of flips, remaining flips will be equal to the following. If I start with N dollars, well, either I will flip ahead, after which I gain an additional $1, right? And after which the expected number of steps left is En minus 1, but I flipped a coin. As a result, I wasted a flip, or 1/2 chance. Okay, so for instance, let's think of N is here. If N is here, the expected number of flips until the game ends is either I go to this or this and the game ends, and let's assume that this is En. Well, one step later, we will either end up at n plus 1 here, or at n minus $1. And that's exactly what I'm saying. So if I end up flipping a tail, I will go back to this spot, after which the expected number of steps remaining will be en minus 1, or 1/2 chance I will flip ahead, after which the expected number of steps needed is en plus 1. And in both occasions, I wasted, regardless of the outcome, I wasted a flip. And that's it. This works for all n. And well, obviously, whenever n is 0, the game already ended. So the E0 is just 0, if you will, right? So if you already start with $0 in your pocket, how many flips is needed? 0 flips. If you start with $28 in your pocket, meaning your opponent has $0, again, E24 is also 0. Do you guys see that? And that's it. So this is a recursion. We are given some initial conditions, and we want to solve for it. Okay, let's go ahead and do that. I can repeatedly write the equations, actually. I can start with E1. So expected number of steps, if I start with $1 and my opponent has $27, right? So the same rules will apply. Actually, you know what? The one inside the parentheses here, I can just take them outside the parentheses. So this can be written as this: 1/2 en minus 1 plus 1/2 en, oh, well, sorry, we are doing it for E1, sorry for that. So E1 is just 1/2 chance I will end up at E0, or 1/2 chance I will end up at E2, right? So I will end up at this location, at the location 2, after which I know that there is E2 flips needed to finish the game, right? But wait a second, if there's a chance, like if I flip a tail and I have no money left, so we already calculated E0 was just the 0, so we can just drop this. And then there's still a plus 1, sorry. So because we decided to take that 1 outside the parentheses. All right, so that's pretty. If you guys want, we can even write it like by multiplying by 2. I think it's more convenient to multiply the whole thing by 2. So let me write it like this, if you want. There you go. Oh, wait, sorry, that's a 2. There you go. I could have, okay, let me just multiply 2 over here so that you guys see the equations. En minus 1 plus En plus 1 plus 2. Yes, that's the equation. Okay, now I can repeatedly write out all the equations, and that's it. We will end up with a system of equations. So 2E2 is equal to E1 plus E3 plus 2, right? 2E3 is E2 plus E4 plus 2, and so on. That's pretty neat. We can go all the way. 2E26 is equal to E25 plus E27 plus 2. 2E27 is equal to E26 plus E28, which is just a 0. So just like E0, I don't need that one, plus 2. So these are my equations. So in total, we have, well, I don't know how many equations we have here. Well, oh, sorry. The first one starts from here. All right, there we go. So we have in total E1 through E27, 27 equations, 27 equations. So how should I solve this? There's there's a couple of different ways to solve this, but does everyone agree on what I did? Do you guys agree with this story here? Okay, so the story was, anytime I am in a position with n dollars, the expected number of flips to finish the game is En. If I have n plus $1, the expected number of flips I need to finish the game is En plus 1. And here is En minus 1 if I have only n minus $1 with me. So because I started at this position today, after the flip, I will end up in either one of the positions with 1/2 chance, but because I did a flip, I wasted a turn, and that's why the plus 1s. All right. Any ideas how to solve this? I'm sure you've seen this one before. Yes, okay, good. Add the equations, perfect. Let's go ahead and add the equations, and let me change my marker. Okay, good. I love changing my markers. So when I add the equations, let's think about it. This is accounting now. bookkeeping, as I call it. Let's do some bookkeeping. Let's check the E1s. How many E1s on the left-hand side? How many E1s on the left-hand side? Yes, clear chat, please. 2 E1s on the left-hand side. How many E1s on the right-hand side? 2 E1s on the left-hand side. Yes, only 1 E1 on the right-hand side. So therefore, ultimately, when you add up all these equations, there will be a single E1 on the left-hand side. Let's check the E2s. How many E2s on the left-hand side? How many E2s on the left-hand side? That's right. 2 E2s on the left-hand side. How many E2s on the right-hand side? Yes, the E2s will just cancel each other. There will be no E2s left. In fact, there will be 2 E3s on the left side and 2 E3s on the right side. So E3s will cancel out. E26s will cancel out with the previous. So E27, there will be 2 on the left, a single one on the right. So there will be a single E27 left on the left side. And on the right-hand side, we have a bunch of 2s. How many of these 2s do we have? I think in total, yes, 27 of them. 27 times 2, 54. 2 times 27 is equal to 54. If we just add the equations, that's what I can get. Remember, what was the definition of E1? E1 is you have $1. How many times should we flip a coin until one of us lose the game? And E27 is if you start with $27 and your opponent has a single dollar, how long until one of us lose the game? Something is happening here. What is that? Yes, that's right. Symmetry. E1 or E27. Well, they are not exactly the same in terms of here you lose and here you win, but the question doesn't care if you lose or you win. The question says expected number of flips until the game ends. So if the game you start with $1, your opponent starts with $27, the expected number of steps until the game ends is the same with you starting with 27 and your opponent starting with 1. That's right. So E1 is just, E1 and E27 are the same. So E1 plus E1 is equal to 54, suggesting that E1 is just 27. Aha. So now the question was asking for E14. How do I find E14? Expected number of steps until the game ends if we start with $14. I have $14, you have. What is the algorithm I should implement? Okay, plug into the equation, which one? I can plug this into which equation? Yes, you guys can write the questions on the chat box. Yes, I can definitely plug this into the very first equation, right? Let's quickly do it. 2E1, so 2 times 27, oops, that's a 2, is equal to, wait, 2 times, sorry, what am I doing? Not that one. Yes, the first one, yes, you're right. 2 times 27 is equal to E2 plus 2. Aha! E2 from here comes out as what? 54 minus 2, 52. Do you guys see that? And then this is like a zipper. How do you unzip? Well, we can go to the second equation now, right? And we can calculate 2 times 52 is equal to E1 plus E3. E1 is just 27. Plus E3, which is the one that I need to calculate, plus 2. And sure enough, from this, we should get that. So what do we get for E3 here? E3 would come out as 104 minus 27, 104 minus 27, 77 minus 275, I think. Do you guys agree? Yes, 75, everybody agrees, yes. And we keep going on and on like this. Let's do one more. Maybe there's a pattern. Do you think there's a pattern? So the next one would be 2 times, so we can go into this one, 2 times E3 is equal to, 2 times E3 is 75 is equal to E2, which is 52, plus E4 plus 2. And that will give us, that's a 52 here. 150 minus 52 is 98 minus 2. E4 is, yes, 96. Well, let's see if there's an emerging pattern here. So we started with 27. So for instance, the meaning of this is the following. If I started with $1, me, and you started with $27, in average, how long until the game ends? In average, 27 steps until so 27 flips. It's very counterintuitive, right? Because even if I did flip by mistake a tail, I lose already, right? But there's only 1/2 chance of that happening where we end in after one step. There's 1/2 chance I will flip a head, after which, so do you guys agree that this solves if I started with $1 and you started with $27? Here, this one solves me starting with $2 and you starting with $26, and so on. Yes, we just look at the differences. 27, 52, the difference is 25. This one, the difference is 23. The difference here is 21. So you can work out these equations all the way to E14. And if you calculate E14 by keep adding those numbers, so starting with 27, we will add 25, 23, 21, all the way up to, so we need to add how many numbers? 13 numbers, right? Because we start at E1 and we want to go all the way up to, so we want to add 13 numbers. That's the first one, the second one. I think we add all the way to 1, right? Is that correct? Yes, there are 13 numbers here. And if you added these, you would have gotten 196 indeed. Whew. Okay, 196, that's the largest. So for instance, if the question is asking for E15, you start with $15, your opponent starts with $13. That's the same thing as E13 because of the symmetry, right? And you can easily make the calculations accordingly as well. So that's a pretty good deal. All right, so that answers this question, this Mandelbrot problem. But in general, this answers pretty much all the this gambler's rune problem in general. So you can find variations of this as well. So let me go ahead and wrap up the story about random walk. So random walk. Last week we did quite a few stuff about random walk. I just want to wrap up with like concluding remarks, if you will, about the idea of random walk. And it is the following. I have, let me come up with yet another question. And the question is very simple. The question is this. Suppose that I'm on a number line. I start at the number 0. Yeah, I did the calculations earlier. I don't want to mess up my calculations. Where did I put my calculations here? Well, okay, so let me write out the equation, and while you guys are looking into it, I'll check my calculations. But the question is the following. So you start at 0, and at each move, you can either go left or right. So you can either go to 1 or -1, just like in the previous case, 2 or -2, and so on. Okay, a couple of things. After 10 moves, after 10 moves, the question is, what is the probability that you will come back to where you started? That's our starting point. After 10 moves, what is probability of back to start? Okay, so that's my first question. I have 2 more questions. All right, so let me give you a minute while I find my solution. Where did I don't want to rework out all these silly calculations again. Okay, I cannot find them, which means I would have to redo it. Uh, okay, my table is a mess, as you can imagine. Okay, okay, that sucks. Okay, let me redo everything. Oh gosh, I don't like it. Okay, well, we should be able to do it together, I hope. Wow, okay, so we have a couple of guesses, I guess. Okay, so let's do it. So I can start at 0. What can happen? Okay, so I need to, let's draw the line again. Okay, so that's one way to solve this problem. And I'm doing it on purpose. So let's do it. And I guess you guys already have some probabilities. Some of you guys are suggesting various numbers. So if I start at 0, I want to basically create the whole probability distribution, right? 6, 7, 8, 9, 10. Or I can go as far as -2, -3, -4, -5, -6, -7, -8, -9, -10. All right. So the question says, after 10 moves, what is the probability that back to 0? How many different ways can I go back to 0? Yes. Okay. Okay. So there's quite a few good things you guys did. Okay. So yeah, I totally agree with. I think Forrest has a very good way of attempting it as well. So obviously, because we are making 10 moves and we can either make left or right with equal probabilities, the desired probability will end up 1/2 to the 10. This is everything. Well, okay. Or let me write it like this. 2 to the 10 in the denominator. Remember that probability is just success over everything. So now success is how many ways can I go back to 0, right? After 10 moves. So going back to 0 means 5 right moves and 5 left moves. That's right. That's pretty much it. So therefore, it is just 10 choose 5 ways. That's it. So all you do is you reorder. For instance, you can have right, 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 left, right, right, left, 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 left. You started at 0 after, so these 10 moves, you go back to where you started. I think that's clear, right? All right. So therefore, oops. Okay, let me just, okay, get rid of that. And if you calculate this probability, okay, what is 10 choose 5? Does anyone know 10 choose 5? 252, thank you. 252 divided by 1024. So this is roughly 1/4, right? Roughly. So this is roughly equal to 1. Well, these are both divisible by 2, 5, 12. Further divisible by 2, 63/2. What's that? 2, oh, sorry, 5. Yeah, 512, 256 here. There you go. 63/256. That's perfect. So this is after 10 moves, the probability of going back to 0. Now, the second question is the following. After 10 moves, how far are we from starting point, from start? In average, obviously. This is an expectation again. All right, so how far away are we from the start? How about that? Okay, so 5 is a reasonable answer because all you do is you check the extremes. One extreme on one end is -10. The other extreme on the other end is 10 as well. So you are saying that maybe somewhere in the middle, somewhere over here. Some others are saying maybe the answer is just a 0 because, so yeah, it seems reasonable that we will probably not be far from the thing. Though there's a problem because we already calculated the probability that we will go back to 0 is negligible. I mean, not negligible, but 1/4 only. All right, so let's do it. So basically, we will just calculate the expected distance after 10 moves, right? So let's begin. So after 10 moves, what is the probability that we will end up back at 0? You guys did it, and you said it is 63 over 256, right? Wait. Yes. Actually, let me just leave it as a combination. I think this way is much better. Okay, so let me just move. So yeah, so this is 10 choose 5 divided by 2 to the 10, right? Do you guys agree that 10 choose 5 10 choose 5 divided by 2 to the 10? I will be back to 0, so therefore I will be 0 away from the origin. Or I can end up at where? Can I ever after 10 moves end up at 1? What's the probability that I will end up at 1 after 10 moves? That's not gonna happen, right? There's no way after 10 moves I can end up at an odd location, right? So I have to end up in one of the even locations. That's right. So I will end up either at 2 or 4 or 6 or 8 or 10. For instance, what is the probability of me ending up at 10 after 10 moves? What's the probability of this happening? Yes, that's right. So 10 choose 10. All moves should be right. So 10 times you have to randomly choose the right, divided by 2 to the 10. How about at 8? What is the probability that after 10 moves I will end up at 8? Meaning I have 9 rights and 2 lefts, right? Oh, no. 9 right, 1 left. What is the probability that I will end up there? That's right. So good. So that would be 10 choose. So we said 9, right? So 10 choose 9 divided by 2 to the 10, right? And then this one ending up at 6 would be 10 choose 8 divided by 2 to the 10. Do you guys agree? I don't need those things. Okay, so those calculations, let me just get rid of them. So we already, so I'll just leave that initial probability over there. So, okay, there you go. So this is the initial probability, going back to 0. How about starting at 0, ending up at 4? Do you guys agree that in order to end up at 4, I need to have how many right and how many left in order to end up at 4? How many right, how many left? Yes, 7 right, 3 left. That's correct. 7, 3, right? Because if I do 7 rights, I will end up all the way. I can go technically all the way up to 7, and then 3. Yes. So therefore, this is 10 choose 7 ways to arrange all these rights and lefts divided by 2 to the 10. And now I know the game. Hey, that's really convenient. The probability of me ending up here is 10 choose 4, 4 rights, 6 lefts, 2 to the 10. This one is 10 choose 3, 2 to the 10. This one, 10 choose 2, 2 to the 10. This one, 10 choose 1. 1 right and 9 left. How many ways can I organize them? 10 ways divided by 2 to the 10. And finally, the probability of ending up here is 10 choose 0. No right, all of them left. There's only one way to do it, and this is the probability. That's it. So now when I do the expectation is very straightforward. These are the probabilities. I will multiply probabilities with the distances. That will give me expected value. Expectation means weighted average, where the weights are the probabilities. Awesome. So the probability that I will end up, actually, let's go organized. Okay, so I will either end up at this point, I will be a distance 10 from the starting point with this probability. 10 choose 10 divided by 2 to the 10. Or I will end up at this point with this probability, and after which I am 8 units away from the starting point. 10 choose 9, sorry for that, 10 choose 9 divided by 2 to the 10. And then, or I can end up at a 6 here. I'm 6 away from the starting point. 10 choose 8 divided by 2 to the 10, the probability. Or I can be at this point, after which I am 4 units away from the starting point. 10 choose 7 divided by 2 to the 10. Or I can be at 2. So I am 2 times 10 choose 6, 2 to the 10. Or I can go back to here. So I'm 0 away from the starting point, 10 choose 5 over 2 to the 10. We did it in the first part of the question, this probability, plus, or I can end up at minus 2, which is 2 units away from the starting point. 10 choose 4, 2 to the 10. 4 times, I can end up at minus 4 with 10 choose 3, 2 to the 10. You guys see where I'm going. 6 times 10 choose 2, 2 to the 10. 8 times 10 choose 1, 2 to the 10. And finally 10 times 10 choose 10. Sorry, 10 choose 0, I should say. 10 choose 0, 2 to the 10. That's the answer, basically. This is the expected distance, right? So the weighted average distance from your starting point. And this number is decidedly positive. It's not 0. The answer is definitely not 0, right? So one thing we can do to simplify the work is we can get rid of that 0. And then we realize that they come in pairs, right? So that will simplify the calculation. So these two are pairs. Why? Because 10 choose 0 and 10 choose 10 are equal to each other. And they both have this 10 coefficient. And, oh, by the way, something else that we should consider, all of them has 1 over 2 to the 10. Let's just take that out first. And then that pairing business 2 times, open parenthesis, we have 10 choose, let's just leave one of them, the smaller one, plus this one and this one are a pair. Oh, sorry, this one had a 10 in front of it as well. Plus 10 choose 2. Sorry, 10 choose 1, I should say. 10 choose 1 times 8, plus 10 choose 2 times 6, plus 10 choose 3 times 4, plus 10 choose 4 times 2. And that's pretty much it. That's how far we will be. All right, so let's just wrap up everything. So 2 times, so there's only 2 to the 9 left here. I can factor out 2 furthermore. So let's factor out another 2 here. So what's left inside is 10 choose 0 times 5 plus 10 choose 1 times 4 plus 10 choose 2 times 3 plus 10 choose 3 times 2 plus 10 choose 4. Okay, let me give you a few minutes to calculate the desired result. And in the meantime, let me check my notes because I don't want to redo this whole thing, but I keep saying that, but then why did I do it? I calculated earlier, huh? Well, okay, apparently I didn't. Anybody calculated it? $2.6, was it that? I thought it was slightly different. Okay, so we have a couple of different claims. 325 over 128, they say. Okay, I'm willing to accept this. Let me see. So we have 1 over 2 to the 8, and inside parentheses we have 5 plus 4 times 10, so that's a 40, plus 3 times 45, plus 2 times 10 times 9 times 6 over 3 to 1. So those two will cancel. And finally 10 choose 4, which is 10. Wait, yes. 10 times 9 times 8, 7 over 4, 3 to 1. There you go. So what we are left is 2 to the 8. So we have a 45, 3 more 45, so 4 45s. So that would be 180 plus 90 times 2, which is 180, plus 4 to 8. There's a 3, 210. So that's 1 over 2 to the 8, 360, 570. Okay, I'm definitely not sure what I did here. Did I mess up? I probably did. Wait, 21, 210. That one is 210. That one is a 90, 180. Oh, that was an 8. Holy. Okay, thank you. Okay, I messed up. Of course I did. All right, so the 3, this one is a 3. That one is a 4. Okay, so that's 120, 240. So this one is a 240. There you go. 240. What do they add up here? 450, 650, 630. Yes. Oh, wow. You guys were right, I think, after all. So 630 over 256, divide further by 2, 315 over 128. That's right. So this is roughly equal to what? 2 point what? 2 point something something? What do you get? Okay, I don't have a calculator with me. Maybe 2.6-ish, 2.4? Oh, okay. 256, yeah, 2.4-ish. Yes, I agree. Thank you. So we will be roughly 2.4 away from where we started, right? So that's a pretty good deal. You can see variations of this problem, right? So let me show you one quick, oh wait, do I wanna, okay, so let me show you one more variation of this, but I will continue with this previous problem. Just side note, what if this was two-dimensional? And what if we were, so we start at the origin of the Cartesian plane, and we will flip, no, not flipping anymore. So we have three moves, and each move is either up, down, right, or left. The question is, how far away are you from the origin after three moves? How far away are you from the origin after three moves? We can either make three ups, so we can go as far as this. We can make three rights, extreme case. We can have three downs, at -3 we can end up, or we can have three lefts, we can end up at -3 as well. So, and we can pretty much end up anywhere on this line as well. Do you guys agree? So for instance, we can end up with one left, two up, or we can end up here. I'm just utilizing symmetry here. We can end up in any of these points, or we can end up in any of these points, right? Where else I can end up? So I can end up at -2, 1, -1, 2. So I can end up in any of these points, 1, 2, and so on, 2, 1. So this is the Cartesian plane, the x-axis, the y-axis, and the question says, in average, how far away are we from? I can't go to 1, 1 because I'm making three moves, but I can end up somewhere else. Oh yes, I can definitely end up in those vertices as well. Do you guys agree? So there are two layers that I can end up with. I cannot end up at the starting point for sure. That's it. Those are all the points that I can end up with. The question is, how far away are we in the end? So I think by now we understand how to solve this problem. First, we need to calculate individual probabilities of ending up in any of these points, right? And then we will multiply with their individual distances. Are you guys ready? Let's quickly do it. So because each of them will have the denominator what? What will be the denominator in each of these occasions? Because we have four moves available for us, whenever we start, we can go to any of the four directions. Yes, it would be 4 cubed, right? 1/64. So I will just ignore the denominators from now on, okay? So it will be just 4 times 4 times 4, which is, yes, 64. So how many different ways can I end up here? All I care is the numerators. How many ways can I end up at this point? Yes, there's only one way. So basically this probability is 1/64. This one is 1/64, 1/64 here, 1/64 here. That's right. How about how many ways can we end up at this point over there? For instance, one way to end up there is right, up, up, or up, right, up, or up, up, right. 3 ways. So therefore, the probability here is 3/64. The same thing here, 3/64, 3/64, 3/64. Yeah, 3 for each one. Each one has a, so these are the individual probabilities, 3/64. How about the probability of ending up in any one of these four? Because of symmetry, they will all be the same. So how many different ways can I end up at 1, 0? Can you give me a sequence of up, right, down that will end up at 1, 0 here? At that point, 1, 0? Two ways, three ways. Up, up, left won't end up here. Yeah. I want to end up here. how many ways can I end up here? For instance, a legitimate sequence would be right, right, left. So right, right, left would end up there. And any combination of these, right? So 3 ways here. So it might be right, left, right, or left, right, right as well. 3 ways I can do this. What else can I do? Can you give me another sequence that could work? Ah, okay, good. You guys did it. Okay, good. So another alternative way would be up, right, down. Do you guys agree? Yes. Right, up, down, or right, left, down. Oh, sorry. No. Just right, up, down. Yeah, that's it. Just right, up. How many ways can I order right, up, down? How many ways to order right, up, and down? There is, yes, 6 ways. 3 factorial ways. That's it. So in total, there are 9 ways. So the probable, and we want to make sure our calculation is correct by adding up all these probabilities. 9 over 64, sorry for that. 9 over 64, 9 over 64, 9 over 6. Let's double check if the probabilities add up to 1, first of all, right? So the corners here, we have 4 of them. So 4 times 1 over 64. 4 times 1 over 64, plus we have these vertices over here. Let me use this color. We have these 8 vertices, yellow vertices here that we might end up. There's 8 of them. Do you guys agree? And each one is 8 of them. Each one is 3 over 64. And finally, we have the 4 inside these 4 here. Each one is 9 over 64. Do they add up to 1? Let's check. 4 plus 24, that's 28, plus 36. Indeed, they do, right? So that's 1. Okay, so our probabilities are correct. Now let's calculate expected distance. That was the question, right? How far in average away are we after we make 3 moves? Okay, we will pretty much employ the same symmetry here. So we will be at a distance of 3 in either one of these corners, right? So 3 away with probability 4 over 64. Or we will be in one of those yellow points. What is the distance of these yellow points to the starting point? Any one of these yellow points to the starting. How far are we from the start if we are at the yellow point? It's not taxi cab distance. It is the actual distance. Actual distance, like Euclidean distance, not taxi cab distance. Yes. Do you guys see? It's square root 5. That's correct. Thank you, guys. Yeah, so square root 5, we have 8 of these points. Each one is 3 over 64. So 3 over 64 times 8 is 24 over 64 root 5 plus, the distance is root 5. And what did we say? 24 over 64. And finally, the distance can be just a 1, right? We can end up in one of the interior points where the distance from the starting point is a 1. And this will happen with probability 9 over 64 times 4, which is 36 over 64. That's it. So we can factor out this 1 over 64. There's a 12 here, a 36 more. So that's 48 plus 24 root 5. And that's simply, I can factor out a 4, I think, 1 over 16. 12 plus 6 root 5, actually I can factor out another 2, 1 over 8, 6 plus 3 root 5, that's it. And what is this roughly equal to? So this thing is like 2.3, this is roughly 7 plus 6 is 13 over 8, right? So this is roughly 13 over 8, which is, I don't know, is it 1.6? Yeah, I think we are roughly 1.6 units away in average from our starting point if we do this random process at the end of this random thing, which is, yeah, nice. So expected distance, again, the way we calculate it is we calculate individual probabilities and the distances when under those probabilities, and we add them up. This is called a sum product. Whew. Okay, so that was pretty good. So I wanted this as a side note. Okay, so back to our problem. Remember the original problem we were dealing. So far, we answered 2 critical questions. If you start at 0, what is the probability that you will go back to 0 after 10 moves? Not only we learned that, but we calculated every probability ending up at -10, ending up at -8, ending up at -6. The reason we needed all these probabilities is to answer that second question. After 10 moves, how far away? Oops, let me just get rid of Okay, there. So after 10 moves, how far away are we from the start? We calculated the expected distance, and the expected distance came out as, I forgot, oh yeah, 2.4, roughly 2.4 units. One last thing related to this problem is the following. So what if we introduce some asymmetry? So suppose that, and then whenever there is asymmetry, then we can talk about probabilities, right? Suppose that again, we start at 0, and again, the same rules. Randomly, you either go one right or one left with equal probabilities. Let's say 1/2 chance. So each one is 1/2 chance. You can either end up at 1 or -1 and so on. The question is, what is the chances that, oops, come on, okay, 5. What is the chances, so there's a -2, -3, let's say all the way up to -10. What is the chances that I will reach 5 before I reach 10? So this is the third question. What is the probability under these circumstances? It's symmetric, fair game. I reach +5 before -10. Is it more than 1/2 or less than 1/2? The answer. More than 1/2, right? Because 5 is closer to 0 than -10 is. So we are expecting an answer somewhere between 1/2 and 1, right? It's definitely not symmetric anymore. And that's why it's a perfect question to ask a probability, right? So how would we answer such a question? I suggest we can pretty much use the same framework we did use in the previous question when we started that gambler's rune problem. Do you guys think, oh, wow, you guys did amazing. Yes. The answer is actually 2/3. Yes. It's totally dependent on the distances. That's it. So because this distance, it's 1 to 3, 1 to 2. So yes, that's right. So 2/3. And there's a very neat way of doing this, and it's the following. So the probability of you winning if you start at a point n, the probability of you winning if you start at a point n is equal to 1/2 chance afterwards you will end up at n+1, the point n+1, after which this will be your new probability of winning, or 1/2 chance you will go leftward, and afterward your probability of winning is p of n-1. Do you see that? And actually, you know what? I can even rewrite it in this following way. Pn is equal to Pn +1 plus Pn-1. Now, that's interesting. So the reason I'm saying that is the following. Okay, so let me just do it like this. So what is the probability of me winning if I start at -10? What is the probability of me reaching 5 before I reach -10 if I start at -10? So basically, I want to calculate P -10. Okay, let me put the word again. So P -10 means me reaching 5 before I reach -10 if I start at -10. So the n here is the starting point in a sense. Yes, that's a 0. And what is, what is the probability of me reaching 5 before I reach -10 if I start at 5? If I start at 5, me reaching 5 before I reach 10 is 1, because I start at 5, right? I already reached there, right? Yeah, it's like, what is the probability of me going to heaven if I start at heaven? But then there's a problem. There's a bunch of probabilities between them. -8, -7, probability of -6, -5, all the way up to probability of 4, sorry, 3, probability of 4, and so on, right? So what is the kind of the good idea that will help me finish the problem? This is P -10, this is P. Our question is asking for P0. If I start at 0, what is the probability that I will reach 5 before I reach -10? And you guys suggested, some of you guys suggested the answer is 2/3. Why could it be? Yeah, you guys are going into randomization things. Oh, 10 choose 2 means you have 10 objects, you choose 2 of them. So the first one, you can choose it in 10 different ways. The second one in 9 different ways. But then order doesn't matter. You need to divide by 2. So 10 choose 2 means 10 times 9 over 2. All right, so what is the good idea? The good idea is the following. Okay, let me tell you what is the good idea. What type of sequence is that sequence? P minus 10, P minus 9, P minus 8, P minus 7. It is propagated by this equation. What type of a sequence is this? If you checked our algebra class last week, you would suddenly notice that this is a special sequence. This is no random sequence here. What type of a, yes, do you guys see that? It's an arithmetic sequence. Look at these equations. So we are saying that the middle term is the arithmetic average of the other 2 terms around it. So this is an arithmetic sequence, starting at 0, ending at 1. You know that in an arithmetic sequence, the common difference is, it's a common difference. The differences between 2 consecutive terms are common, right? So the gap here is D. The gap here is D. The gap here is D. How many gaps are there between these how many terms? 16 terms. There are 16 terms. How many gaps as a result? What's a no? I messed up again? Yes, 15 gaps, and that's it. So the gap length is equal to, because we are moving between 0 and 1, the gap length is 1 over 15, and that's it. So our initial term is 0. P10 is 10 gaps away from, sorry, P0 is 10 gaps away from P minus 10. So therefore, because P minus 10 is 0, the answer is P0 is 10D, which is 10 times 1 over 15. That's just 2/3. Aha! That's pretty neat. All that it depends is this equation. Interestingly, the previous problem, the gambler's rune problem, that had a slightly different propagation thing. Remember, in the gambler's rune, there was a +2 here. That because of that +2, it didn't exactly evolve the way this one evolves. But because of this one, so the gambler's rune problem, let me go all the way up. Where was it? If you check that equation, oh yeah. So do you see that this one is not exactly like that, right? So look at that. So there's a +2 here in each one. It's not exactly an arithmetic average. That's why we had those gaps differ. So this here, it was at 25, then 23, and so on. Do you guys agree, huh? All right. And then that's pretty much it. So now you know if you have, under these circumstances, it depends on the distance. If it's a fair game, obviously we can make this question more challenging. What if the right probability is 2/3 and the left probability is 1/3? Then what is the probability that starting at 0, you will end up at 5 before you end up at -10? Okay, I'll leave it to you guys to do that. All right, so this is already pretty, I think for some of us, it might have been advanced. But yeah, so that was good so far. All right, so in the remaining 30 minutes, what I want to do is I want to solve 2 puzzles with you, probabilities, both of them, and then I'll give you another homework, all right? And then next week, we can continue with that homework question. All right, so the 2 puzzles. The first puzzle is, before that, I took notes here that, okay, there is this problem that I wanted to remind you because, okay, this thing, I think it appeared a couple of times and I kind of ignored it. And it is this idea of, quickly, I won't go into detail about this technique, so linearity of expectation. In fact, in some of the problems, the calculations could have been simplified if we did use this technique. It's called linearity of expectation. And there's a very old American high school math examination problem. I think it was from 1989, and you can check it on AOPS website. Let me quickly tell you this question, and then we can move on. So I wanted to make sure of that one. So the question says the following: there are 13 girls and 7 boys. You put them in order next to each other in a row of 20 chairs, 5, 6, 7, 8, 9, 10, 16, 17, 18, 19, 20. Okay, so you are sitting them around, on those chairs, and the question is, you are randomly putting them here, right? The question says, in average, how many adjacent pairs adjacent people will be girl boy or boy girl pair. For instance, okay, just as an example, maybe the boys are spread out like this: boy 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 boy. How many boys? 1 2 3 4 5 6 7. Okay, and then everything else is a girl, right? So let me put a dot for girls, so it's easier than write a G, the letter G. Okay, there you go. Then the question is, so for instance, here the count that we are looking at is the following. So how many adjacent pairs? So 1, we have a girl-boy pair. There's another girl-boy pair, that's a 2. That's a 3, a 4, a 5, a 6, sorry, a 7, 8, 9, 10. For instance, in this example, that's 10. But there are 27 ways to arrange them. And in this particular ways, it is a 7. So therefore, the question says how many pairs. The expectation would have been the following, right? You calculate 20 choose 7, which is a huge number, and you add them up. Here in this example, it's a 10. In another example where I put all the boys together, 7 boys together, and all the girls together, the answer is just 1. It can go as low as 1 or as high as, if you alternate them, like girl, boy, girl, boy, girl, boy. What would it be then? If we alternate them, because we have 7 boys, on either side you can sit girls. For boy 1, on either side it will contribute 2. I think the max would be 14, right? So you have all these numbers. The question says, in average, if you randomly place these boys and girls on that line of 20 seats, in average, how many pairs will be boy-girl or girl-boy pairs will you have? Come on. What's the key idea here? How should I approach it? What's the key idea? Huh? The key idea is to look at something. What is it? How long is class? The class ends at 3 p.m. Yes. Okay, so some of you guys, I think, oh no, yeah, there it is. I think the key idea is the following. So what linearity of expectation is telling you is the following. Linearity of expectation tells you that, you know what, you can just look at an individual location here. So let's check the first pair. All I do is check the probability that the first pair will be boy-girl or girl-boy, and then just add each of these probabilities, basically. So the probability of the first pair, seat 1 and seat 2 will have opposite genders. The probability that seat 2 and seat 3 will have opposite genders, and so on. Now, this is an extremely subtle idea. So basically what we are saying is the expectation of, if you have 2 random variables of x and y, the expected value of x plus y is just the expectation of x plus the expectation of y, even though what? Even though x and y are random variables, even though x and y are not independent, this works. Isn't that amazing? This is not the case if, for this one, ex times y is not equal to ex times ey. And it's very easy to calculate, I mean, to give examples to it, but this one is true regardless. So that's kind of a subtle idea that a lot of people have kind of, like it's, I mean, it's not clear. Intuition, this is one of the areas where intuition is kind of lacking behind the math, the algebra, I guess. But anyhow, so based on this, then we do the following. The probability that the first 2 seats will have 2 people with opposite genders. Well, first of all, for those 2 seats, I can choose 20 choose 2 ways. I can choose those 2 students. And how many ways can I have a boy and a girl where order does not matter? So, oops. Let me just do it like this. 7 choose 1 way, I can pick one of the boys. 13 choose 1 way, I can pick one of the girls. Order doesn't matter, and boom. So that's the probability that this pair, the first seat and the second seat, will be occupied by opposite genders. And all I do now is just to multiply this number by 19, because there are 19 consecutive pairs. Do you guys agree? Okay, so this is one of the deep ideas that a lot of times it makes the calculations a lot faster than otherwise, right? So that's one thing that yeah, so that you should be considering. There's so many like applications of this that I'll just leave to you guys to later on have a look into that, right? It's 9 and 1. All right. It's 9 and 1 over 10. What is 9 and 1 over 10? Okay, I might have messed up. Okay, fine. All right. So and this is equal to, I think, 91 over 7 times 13 is 91. 20 times 19 over 2 times 19. The 19s will cancel. 20 over 2, that's a 10. So the answer is 9.10. 9.1. So in average, we're expecting 9.1 pairs of boys and girls sitting next to each other, which is kind of reasonable. The highest is 14, the smallest is 1. So therefore, it should be somewhere between them, so which is reasonable, I think. Awesome. So I wanted to make note of that. One more thing that we kind of might have used in one of the previous questions that we didn't because the number 10 was so small. What if the question says that after 100 moves, how far away you are from the origin? At some point during the calculations, you end up needing a combinatorial identity like this. Let me show you the combinatorial identity, and you tell me what it is equal to. I mean, what is the interpretation? I love combinatorial identities. So the claim is this: n times m minus 1 choose r minus 1, or let's say k minus 1, is equal to what? K times n choose k. How about that? How do you prove such a thing? Why is this true? I claim this is true all the time, where n is greater than or equal to k, greater than 0. What is the interpretation behind this? Do you guys agree this is true? We can test it. I mean, for instance, n is equal to 5 and k is equal to 3. So the claim is that 5 times 4 choose 2 is equal to 3 times 5 choose 3. And sure enough, on the left side, we have 5 times 6 is equal to, on the right hand, we have, yeah, 3 times 10. It works. It seems it works. What is the logic? Why does this combinatorial identity works? So what are we, okay, let's do it one step at a time. What does the left-hand side counts? What are we counting on the, or let's count the right-hand side. Right-hand side is easier to count. What are we counting on the right-hand side? Yeah, it's extremely familiar. What is it that, n choose k? N choose k counts what? Let's start with n choose k on the right-hand side. What are we counting n choose k when we say n choose k? Yes, the number of ways to choose k objects from among n of them, or k people from among n of them, right? You have n people, you want to choose a committee of k people. Why would you multiply that number with k later on? What does that multiplication do? So you have chosen k people from among n people. By multiplying by k, what do I do? So those k people, I choose one of them as the leader. Yes, choose a president. So among the n people, you selected a committee of k of them, and among the k, you select one of them. So this is like k choose one in a sense. That's it. How alternatively can you have done those selections? How about on the left-hand side? Yes, first choose the leader. Once you have the leader, you have n minus 1 people left in the public, in the population. You want to still choose k minus 1 other people to serve in the committee. In fact, one of the questions we did earlier, the generalization makes use of this combinatorial identity. That's it. So just keep that in mind. Those type of combinatorial identities are useful in terms of manipulating like combinations and so on. All right, so that's it. So next, I have two back-to-back combo problems. Let me see. Yeah, so probability questions, I should say. One of them is the following. Let me see if I can find my question. Uh, oh yeah, I found it. All right, so the question is this. You have two buckets. We're gonna play a game, two buckets. One of the buckets has two red, 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 and then one black ball, black. The other bucket has one, okay, I'm not gonna draw 101, so 101 red and 100 black balls. All right, so two buckets. But from outside, you can't distinguish which one is what. Okay, so these are, you can think of these as closed black color bags. Both of them look similar. All you're allowed is pull out something from inside. So this is a problem. Okay, so the problem is the following. You play the following game where the goal is to maximize your chances of guessing something correctly. Okay, so this is an optimization problem. So the person who is creating this game is letting you choose one of the bags, pull out a ball, and then you can see the color of that ball, and then you put that ball either back into the bag, or you decide you want to take it outside, keep it outside the bag, and then draw another ball from that same bag. Okay, from that same bag that you picked early on, pick another ball, and then you are allowed to look what is the color of that ball again. Then the question is, yeah, the question is, which of the bags did you pull out the ball from, the two balls from? Do you guys agree? So the question is, draw a ball from one of the bags, then decide, so this is the part which is important, decide whether you want to do it a replacement or no replacement, or not. That's the part that I'm asking. So that's the question. And then you draw another ball from that same bag, and then the question is, you need to guess which bag you have selected from. So you need to guess if that bag was the bag with 3 balls in it or the bag with 201 balls in it. The question is, in order to maximize your probability of winning in this game, correctly guessing which bag you pulled the thing from, the ball from, should you choose replacement or not replacement? After you draw the first ball, should you put it back into the ball, back into the bag, or should you keep it outside, do not replace it, and then take another ball from that urn? Yeah, so that's a pretty weird question, right? This is more like a game theory problem, I would say, right? So where we have a strategy going on, the strategy is replacement. Which of, like, replacement means you put the ball back into the bag. Don't replace means after you pull the first ball. So this is a 3-step game, right? And choice happens only on the second stage. The first stage and the third stage only lets you see the color of the ball. So based on this, yeah, so which of the two options is the better one? Well, what you can do is we can have a look at it. All right, let me first give you 2 non-optimal ways to look at it, and then there's a very optimal way to do this thing. All right, so this is a really nice problem, and then I'll give you the other question. I don't think we will have enough time to finish with that other question. Ho. Wow, so we have some smart guys in the room. All right, so good. All right, so let's first have a look at the case where we do it with replacement. All right, so if we do it with replacement, we can do the following, like calculate the following probabilities ex ante beforehand, right? So what are the chances? So I'm doing it with replacement. All right, so regardless, I say replacement. So the balls out, it might be either I can have taken a red ball first attempt, red ball in the second attempt, or I could have done a red ball in the first step, a black ball in the second step, or a black first and then a red, or in both occasions, I took out two black balls from the urn. All right, so what is the probability that it might have come from A, such a thing, two red balls in a row coming from A, versus two red balls in a row coming from B? I want to check these individual probabilities and I want to compare them. I want to see which one is the larger one. So what are the chances that I would have chosen randomly the first ball? So suppose that this is urn A and this is urn B. The probability that I would have gotten those two red balls from the first bag, well, first of all, 1/2 chance I picked the first correct bag, bag A. Afterward, like selecting two red balls with replacement is what? Two red balls back to back, because it has two red in it, 2/3, and then another 2/3, right? That's it. Versus, what are the probabilities that I go to the second bag? 1/2 chance I'll go to the second bag, and me picking two red balls is 101 over 201, and then 101 over 201. Do you guys see that? So I'm like, before I even start the game, I'm thinking about what are the chances if I see two red balls in front of me, which one is more likely event that might have happened? So which of the two is more likely? Which of the two quantities is larger? This probability or that one? All right. Yeah, it's relatively straightforward, I think. Huh? I think, yeah, so this one is bigger, right? So you can do an approximation, and I think this is bigger. Why? Because the twos cancel. So on the left-hand side, you have 2/9. And on the right-hand side here, this is extremely close to 1/2, extremely close to 1/2. This is 1/2. So this is close to 1/8. So you have 1/8 over here. This one is 2/9. This is definitely larger. And we can do pretty much the same thing for the others as well. What is the probability that I will first have a red followed by a black? So 1/2 chance I will pick the urn A. And afterwards, 2/3 chance I will get a red in my first attempt, and 1/3 chance I will get a black in my second attempt, versus 1/2 chance I pick the urn B, after which me picking the black is, the red is 1/1 over 201. Me picking the other one is 100 over 201. And indeed, this one is bigger now, right? Do you guys see that? So what I'm saying is, if I picked using that strategy, regardless, I replace. So then if I pick two red in a row, I would probably think that I have selected them from the urn A, so from this one. Versus if I had a red followed by a black, I would have probably selected it from that bag. Do you guys see that? But again, I'm not using strategy in a smart way in these terms. How about black and red, right? Black and red. So in my first attempt, I did, well, first choosing from bag A, choosing a black is 1/3, choosing a red is 2/3. Compare this with choosing randomly bag B was 1/2, choosing a black is 100 over 201, and then choosing a red is 101 over 201. And indeed here again, this one is larger. And lastly, 1/2, two blacks in a row, 1/3, 1/3. This is definitely less than 1/2, 100 over 201, 100 over 201. Independent events. All I will now do is just to add up these yellow things, right? So, and I will just calculate my probability of winning after all these four cases. Oops, come on. All right, so if you added all these yellow probabilities, this thing comes out as 0. Oh, let me write it as a percentage. I did the calculations earlier. It comes out as 59.6%. So 59.6% chance, if I use replacement, I can win. If I use without replacement, we can pretty much do the same calculations. Let me just make it slightly smaller, and let me just do the calculations again here. So the balls that I select, the first round, red, red, or it might be the first round, a red, the second round, I got a blue, or the blue and the black and a red, or finally black, black. So individual probabilities can be again calculated in a similar way. Oops, sorry for that. me just get rid of this one. Oh. Okay, so let me go ahead and do it over here on that side because my chat box is pretty much okay. Oh yeah, there you go. Okay, I can see my chat box again. Yeah, I was just curious what's going on there. Okay, good. So the probability of this coming from A versus the probability of that that might have happened from a B bag. Okay, so a red first, 1/2 chance. Picking up a red is 2/3 from bag A. And after which, because this is without replacement, there's only one red left out of the two, so that's a 1/2. And compare this with 1/2 times picking the red in the first occasion is 101 over 201. And picking yet another red is 100 over 200. If you compare these two, I think it is this one, which is the bigger one. And you can do pretty much the same thing for the other ones as well. 1/2 chance you will pick a red, and then 1/2 chance, 2/3 chance, you will pick a red followed by a black, which is greater than, again, 1/2 chance, 101 divided by 201, and then 100 over 200 balls left here. So you would have picked this one. You would have suggested that this was taken from bag A, and you would have been correct with this probability. Again, bag A, you would have said here. This one would be 1/2 chance you will take from A. Picking a black is 1/3. Picking a red now is 2 out of 2, right? So this is greater than 1/2 chance. The black is 100 over 201. The red is 101 over 200. And lastly, 0 chance for you to pick 2 blacks in a row because it's without replacement. And this is obviously less than 1/2, 100 over 201, 99 over 200. So therefore, the probabilities are, the ones that you will select are these. Oops, sorry for that. Okay, so based on these, if you added those circled probabilities, guess what? The probability of this would have come out as 62.3%. So which means without replacement is better than with replacement in terms of guessing which bag you picked from, right? But then some of you guys already suggested earlier, there's a better strategy to attempt this. What is this? It depends, because I have a choice to decide replacement or not. I don't have to go like regardless replace or regardless don't replace. I can decide to replace or not based on the color, right? So what we can do is we can decide to replace if the first one is a black, if the first one is a red, replace it. And if the first one is a black, do not replace it, right? And so that's it. And you can make a strategy. And then if you do so, okay, so I won't do it because, yeah, it will take way too much time. But so here's a strategy that's still available to you that is, and that might work. So if the first ball is a red, first ball red, suppose that you replace, meaning you put back that ball into the bag, versus if the first ball is black, no replacement, no replacement. If you do the probability here, the probability calculation comes out as 63.7%. It's an improvement. So you have a higher chance of winning this game if it's red, you replace. If it's black, you don't replace. Okay, interestingly, you can do the opposite strategy as well, and I'll leave it to you as a homework strategy. What if the first ball is red, no replacement, and if it is black, replace? What is the probability here? And the reason I gave you this probability, you can still calculate and you can check for yourself if it works or not. All right. Now, last question. So this is actually, okay, so we have about 5 more minutes. Let me ask you the following question. Let me play the game. That's your homework till next time, okay? So next week. All right, so the game is the following. It's one of the fun game you can imagine, and it is the following thing. Again, we are in the Cartesian coordinates. X, Y, the solution I'll show you next week. So we have these grids. Let me just quickly draw the grid here. Okay, There you go. Maybe one more. All right, there you go. So we have 0 here. 1, 2, 3, 4. 1, 2, 3, 4, 5. The question is this. You start with one chip over here. And at each move, you are allowed to remove a chip. In this case, I can remove this chip over here. But anytime you decide to remove a chip, you have to duplicate it. You have to put two new chips, one on the above and one on the right, like this. You guys agree? Then, for instance, so we no longer have a chip here. All right, so that chip disappeared and it gave birth to two of them. Then what I can do is I can, for instance, do the same thing here. I can do a move here where I remove that guy and I can replace it with two chips here. You guys see what I'm doing? So this one is gone now. We have three chips now. So for instance, I can now operate on this one. I can just remove that and add two new chips over here and over here. The question is it ever possible to push all the chips beyond this thing here? Let me just, oh gosh. Yes, I want to remain below this line over here. I don't want any chip even on this line. So all the chips, you need to put it on this side. Can you push all the chips up to that? So I want to go above x plus y equals 3. I don't want any chip on x equals, so we need to keep pushing. For instance, this chip over here, I need to keep pushing it. So for instance, I can just push it. There you go. So it will become like this and like that, right? Oh, luckily, these two are safe now, right? It seems it's doable, right? Wait, can I push this chip? No, because there's another chip above it. I can't, so in any lattice point, you can only allow one chip. So first I need to remove that one if you want, and I can replace it with these two. And then I can get rid of this one as well. So I can get rid of this. You guys see that? So just get rid of this and then put two chips over here and over here. Hey, that's pretty good. So I removed, so I only left with these two guys. Well, this one I can kind of do the same thing. I can just put that one here, that one there, and this one is gone, right? So this is kind of annoying because there's this guy over here, which is kind of won't let me operating on this one. So why don't I first remove this guy, put it one here and one here, and then I can push this guy over here, put one there and one there, and finally I have enough space. I can get rid of this one, replace it with one here, one. Hey, that's pretty good. Well, we still have two problem cases. We have this one is a problem, and then this one is a problem. So we still need to push those as well. So I'm not allowed to have anything remaining. Oh gosh, okay. So I don't want anything in those yellow cells. So nothing over here. I don't want any chip. Right now we have two problem chips, so I need to keep operating on those chips, right? So keep pushing them. One way you can do it is if you have some graphing paper at home, you can, if you have especially like Connect 4 type of chips as well, play this game on that graphing paper and then discuss it with your parents if it's possible to do that. All right, so this is one of the questions, and the same strategy applies to this question. Okay, so everyone understand this? Any question about this game? Okay, have you ever seen this? Do you like these type of games? Here's another game. All right, so this is the first problem. The second problem is very similar in nature. You will see the connection. If you can solve one, then you can solve the other one pretty easily, actually. The question is this. So this is the coordinate plane again. And again on the grid, so we have this infinite grid. Okay, so let me just draw a few of them. Okay, so there we go. All right, so the origin was, wait, where was the origin? This one? Okay, so suppose that this is the origin. So we have chips everywhere, where? Not everywhere, sorry for that. We have chips, and this is, by the way, the starting point. So we have chips everywhere on this here, where y is less than or equal to 0. We have chips, infinitely many, one chip at each lattice point, and you are not allowed to put two chips, by the way. This time the allowed move is the following. If you jump over one chip, so what happens is, because you jumped over that chip is disappearing and this chip is gone, it is moved over here. Do you guys see that? The question is, can you ever reach, using this strategy, so this is y equals 0, y equals 1, y equals 2, y equals 3, y equals 4, y equals 5. Using this strategy of jumping over things, can you ever reach to the level y equals 5? That's it. Okay, let me experiment a little bit. So for instance, so far we reached y equals 1, right? So I can easily reach to y equals 2. I can just move this guy over here above the other one. I can jump over him. So that would place him over here. And as a result, these two are gone. You guys see that? The reason I did that is now I can jump this one over the other one. So it would come here. And so these two are gone. You guys see that? Hey, I already reached y equals 2. It seems it's doable, right? All right, so what I can do, I can jump this one over here. I would have one over there, so these two are gone. I can jump maybe this one over here. So these two are gone. We have one here. I can now jump this one next to it here. These two are gone. They are done. And then finally, I can jump this one over here. Hey, I'm getting super close to y equals 5. Now, again, at home, if you have a graphing paper, that one is gone. This one is also gone. Okay, there we go. So far I did y equals 3. I should be probably able to get to y equals 5, right? Why not? See if you can get there. All right. Is this enough puzzle, or do you want one more puzzle? So the method that we use in both of these is the same. Interestingly, the same method applies to this problem as well. Okay, last problem. So these are all being recorded anyways. Okay, so just one more minute. I'm a little bit over time, sorry for that. The third problem, which you can use the same strategy again. There's a bunch of people around a circle. How many of them? 2020 people. 2020 people around the circle. So person 1, person 2, 3, 4, 5, all the way up to 2020. So in this one, we have the first person, which starts with 2020 chips. Let me write the chips in a different color. So that guy starts with 2020 chips. Each time a person has 2 chips or more, what he can do is he can just give away 1 chip to its 2 neighbors. So in the next move, for instance, there's only 2018 left here, and in person 1, and now these 2 guys have 1 chip each. And then that guy can give yet 2 more. So there's 2016 left here. So this guy now has a 2. This one has a 2. So as a result, what you can do is you can further give chips, right? So for instance, this 2 here can give 2 chips, 1 to the left, 1 to the right. So this person 3 now has 1 chip. And the same thing for that guy. 2020 can give 1 chip here. So there is a 1 here. And then you will give back 1 chip over there. Interestingly, this guy will jump back up to 2018. So now the new configuration is 1, 0, 2018, 0, 1, and everybody else is still 0. Do you guys see that? The question is, will this game ever end? Will this process ever terminate? Ever terminate means, could it be a situation where everybody has exactly 1 chip? If everybody has 1 chip, then there is nothing to do, right? So you can't do further than that, because for you to proceed is, if you have 2 chips here, in the next round, you can give 1 to here and 1 to here. So this one is gone. So there's 1 and 1 here, right? So is it ever possible to end up with a situation where everybody has just 1 chip? That's it. So those are the 3 questions. Interestingly, all 3 of them use the same strategy to solve them. So next time we can talk about these strategies as well. So let me go ahead and stop today's recording. So thank you guys so much for joining today. I'll see you guys next week. So these recordings are also available on our Momentum YouTube channel. And you can check our Momentum page if you're interested. We have quite a few counting classes as well. You guys can double check there as well. All right, so see you guys.